are in this book here, Causal Inference and Statistics, and we are on problem 1.38. Okay, so 1.38 has a lot of parts, and its parts has parts. So let's just kind of get going one at a time here. So the idea here is that we have some kind of game here, kind of like in 1.37. But in 1.37, we were flipping coins, and here we are rolling two die. Two dice? I don't know. And we're recording the outcome of the first die, which is x, as well as the second die, which is z, and then we're summing those together to get the variable y. Okay, so y equals x plus z. Okay, so now in part A, we're going to calculate a bunch of things here, just highlighted here at the top of the cell. Expected value of y, expected value of x, expected value of y given x, and so on. Okay, so so let's kind of step through these. I'll kind of gloss over this so that and you can kind of take a look at it on your own. I just noticed an error. Give me 1 second to fix it. Okay, so let's start with the expected value of x, and now we're also taking the expected value of x to be the same as the expected value of z because we have two dice here. So we're just assuming that they're equivalent. And the formula, you can look it up in 1.37, but it's the probability of each. It's the sum of the products, where the products are the value of x, or the values of the dice 1 through 6, and then the probability of x equals x. Okay, so it looks like this. And it should equal 3.5, right? So the expected value for both x and z should be 3.5. All right. Now the expected value for y, remember y is the sum of x and z, and so you could do the same formula that we just did, but you would have values 2 through 12, and then each of those. And then each of those values they wouldn't all be 1/6, right? So for instance, there's three ways that you can make a 4, right? You can have a 1 and a 3, a 2 and a 2, and a 3 and a 1, right? So you'd have to go through and figure out all of those calculations, or we can just use the fact that expectations sum linearly, or when so since x and z are independent, which they are, their expectations can sum to the expectation of y. Okay, so we can just have 3.5 plus 3.5 equals 7. Okay, so now we have the conditional expectation of y given x. All right, so we can think about this in a few ways. Again, you can go through and you can apply this formula, a variant of that formula, but we can also just think our way through all of this. Okay, so the conditional expectation of y given x means I tell you the value of x, what is your best guess for the value of y? Okay, well, we know that the expected value of y is expected value of x plus the expected value of z. Okay, and we know, so if I give you x, or actually what I should have said is that we know that the value of y is x plus z. So if I give you x, then really it comes down to what is your best guess for the value of z? Well, we already found that the expectation of z is 3.5. So the expected value for y given x is whatever x is plus 3.5, right? Where 3.5 again is your best guess for the value of z. Okay. Now we're asked kind of the reverse. What is the expected value of y given, the expected value of x given y? So this one is, to me, it's a very intuitive answer, but it actually becomes very hard to explain or to justify, okay? But roughly, so the expected value of x given y is the same as the expected value of x given y, and also given that the expected value of x equals the expected value of z. Okay, so in other words, whatever y is, x is probably half of that, right? Because x and z are independent and identically distributed, right? And so, so they're it's most probable. Well, how do I want to say this? Because they are identically distributed, the most likely value for one is going to be the most likely value for the other. Okay. So so anyway, we can actually kind of demonstrate this. It's not really proving it to ourselves, but we can kind of show this to ourselves, right? So if we have y is 4, well, there's 3 ways that we can get y equals 4, right? We can have 1 and 3, 2 and 2, or 3 and 1. And now if I am to take the expected value of x, right? So I know y, right? So I've constrained x to just values of x for which y could equal 4. And if I take the expectation of x here, I get 1 plus 2, which is 3, plus 3, which is 6. 6 divided by 3 is 2, and 2 is, well, it's 4 over 2, or 2 is 1/2 of y, right? So, but you could do this with any value for y, and again, what you'll come up with is that the expected value for x is going to be half of y. Okay. All right. So now we want to find the variance of x. Okay, and so again, the formula for the variance of x is just this guy right here. Okay, so it's the expected value of the squared difference of x minus its expectation. Okay, and so you can run through all of that. Okay, so here's the big long formula written out in all its gory detail, and we get about 2.94 with, there's rounding errors in there. Okay, so now we want to find the variance of y. And we could go through the same process that we just did, but again, we would have not probabilities of 1/6, but different probabilities for each value, and the values of y would not be 1 through 6, they'd be 2 through 12, and the expected value of y would not be 3.5, it would be 7. But you could plug all of those in and you could get, whatever the answer is going to be. But we could also think about this a little bit differently. Okay? So we know that the variance of y, okay, well, we know that y is x plus z, okay? And there is a property of variances that they can sum as long as just sum linearly when the composite variables are independent, and that's what we have here, right? So we have that the variance of the x and y, x and z are independent. And x and z are also identically distributed. Okay, so that means that the variance of y is going to be equal to the variance of x plus the variance of z. And so because x and z have the same variance, we know both of those, right? It's just 2 times the variance of x, which we just found. And so the variance of y is just twice the variance of x, or variance of x plus the variance of z. So it's about 5.23, something like that. Okay. So now we move on to the covariance between x and y. Okay. and so in the previous question 1.3.7b, you can look at the covariance formula and you can go through and you can churn through all of that, and that's fine. But here I want to just take a different tact, just building on what we just did. Okay. So here we know that the variance of y, as stated just now, is the variance of x plus the variance of z. Okay. So we could put that into the English language a little bit better if I were to say something like the amount that y varies with as x varies is 1/2 of the variance of y, and the other half is because of the variance of z. Okay, so that means that the covariance between x and y is 1/2 of the variance of y, which is, again, just the variance. In this case, it happens to be the variance of x, but it's 2.914. Okay, and so now if I want to find the correlation between x and y, well, I take the covariance, which we just found, divided by the standard deviation of x and the standard deviation of y, or I could write that as the square root of the variance of x times the square root of the variance of y, and if you plug all those in, you get a correlation coefficient of about 0.71. Okay, and finally we have the covariance between x and z. Okay, and so again, we could go through the formula that we saw for 1.3.7b, and we could plug all of that in, or we could just recognize that that we've defined x and z to be independent variables. They're two different die. And so, dice, geez, I don't know which it is. But anyway, but by virtue of them being independent, they have no covariance. Okay, so it should be 0. Okay. Okay, now on to part B. Now part B, okay, so let me set up part B. So everything that we just did here is very analytical, and it assumes infinite data or perfect data, okay? But now in part B, we actually ran an experiment, okay? And these are the results that we get, okay? For 12 rules, it looks like. Okay, we have x, die 1, die 2, and then there's sum. Okay. And so now the difference between pristine data or infinite data is that this will converge, or infinite data will converge to perfect data, or the expectations. How do I want to say this? When we sample, when we actually run an experiment and we get sample data, it will not necessarily have perfect fidelity to the theoretical values that we should obtain. Okay, so now we have this experimental data, and so we're going to go through and try to find with our sample data what our average x and our average y and all of these different conditional probabilities actually is, as well as the variance, etc. Okay, and what we're going to find is that the values that we get from our sample are going to differ a little bit, somewhat, from the theoretical values, okay? And so I'm doing this in R, and so if you know R, that's great, and if you want to run through this with R, that's fine too. But if you're going to do that, then you need to come up here, if you're going to do it in the Colab sheet anyway, you need to come up to runtime, and you need to go to change runtime type, and make sure that this is set to R. It's usually by default set on Python. Okay, or you could do it in Python too, but I did it in R. Okay, so so the first thing that I do here is I'm just converting this table up here into a data frame that I can enter into R. Okay, so that's what we have here. All right, and so my data frame is called df, and I have variables x, z, and y. And so now to get my expectations of x, z, and y, I just take the mean of those variables, okay? So now here, recognize that our theoretical distribution says that these should both be 3.5, the mean of x and z, but we don't get that. And that the theoretical mean of y should be 7, but we don't get that. And again, that's because of sampling bias. That's because even though the theoretical distribution has very clearly has very clear expectations of what these should be, when we sample data, we don't necessarily get a completely representative sample. And so, anyway, all right. So now we want the expected value of y given x and the expected value of x given y. Okay, and so you can kind of step through this code, and that's fine. But when you come out the other side, so the expected value of y given x, so I have each value of x, okay, and then the corresponding expected value of y, okay, and then similarly, I have every value of y, 2 through 12, and the corresponding expected value of x, okay, and you'll notice that sometimes there's these NaN, which stands for not a number, I believe. Well, this is just where there was no data in our data set, right? We didn't have data that corresponded to, y equals 3 or x equals 2, etc. Okay. Now we're onto the variances and covariances with our data. All right, so here we have, so you can just kind of follow through with all this. Again, the values that we obtain are they're simply going to be different than the theoretical values that we calculated ahead of time. All right. Whew, that was a lot. Okay, So on to the final three, and these are fairly short. Okay, but given our results in part A, determine the best estimate for y, which was again the sum of x and z, given that we measured x to be 3. Okay, well, if we go back up here, we realize that we came up with an expression for this. The expected value of y given x was x plus 3.5, right? Where 3.5 represents the expected value for z, which is the other component of y. Okay, so when we know all that, and I know that x is equal to 3 plus 3.5, this means that the expected value for y would be 6.5. Okay, so now for part D here, what's the best estimate for x given that we measured y to be 4? And we went through this above, and we found that the expected value of y, or of x given y, is y divided by 2. So here, if y equals 4, then 4 divided by 2 is 2. So that would be our best guess of that would be our expected value for x when we see that y equals 4. Okay, and finally, part E. So what is the best estimate of x given that we measured y to be 4 and z to be 1? Explain why this is not the same as part D. Okay, well, the reason that it's not the same as part D is because we're given this additional piece of information, which is that z equals 1. Okay, well, now the relationship between x and y and z is completely deterministic, right? Y is x plus z. So given this new piece of information that y is 4 and then the new piece of information that z equals 1, that means that our system is completely constrained so that x has to be y minus z, and it must be 3, right? Because we already have these two parts here. We have the x being 3 is the only value that would suffice for our expression. Okay, that is it. Thank you.